Alrighty, remember yesterday we talked about potential energy, and we said that even objects that aren't in motion have a type of energy, and it is called potential energy. Potential energy is that energy that is stored due to the interactions between objects. We talked about only two types of potential energy yesterday, and those are just the two types. There were three in your book, but remember we're only going to cover two. We talked about chemical potential energy. Remember that is the energy due to chemical bonds. And we said that two examples that we gave were the chemicals stored in food, such as sugar. When we chew up and digest food, we break down sugar molecules, and when we break them down, those chemical bonds release energy that we can then use to move our muscles and to have our organs function properly and to have our brain work properly. Another type of chemical potential energy, so the chemical potential energy is the energy stored in those sugar bonds, right? It's not energy that we can actually see or really measure until it's broken down and converted from that chemical potential energy to mechanical or kinetic energy, movement energy, like with movement of our muscles, for example. Then we talked about gasoline. This is the same kind of concept. Gasoline is made up of chemicals, and when we break those chemicals down, energy is released, and that can cause us we could have a fire. That would be thermal energy. So we're converting that chemical potential energy of gasoline to thermal energy. We could convert the chemical energy stored in gasoline. We could put that into a car. And the car could turn that chemical energy into kinetic energy by movement, right? Having the car move. All right, so those were the two examples we gave for chemical energy. We then talked about gravitational potential energy. And remember, this is energy due to gravitational forces between objects. And we had an equation for this special relationship. And that is GPE, measured in joules, or gravitational potential energy measured in joules, equals the mass times the gravitational strength times the height, how tall or high up the object is from whatever our relative point is that we're discussing. We did several example problems of that, and last night your homework was all about potential energy. So what we're going to do today, I'm not lecturing on any new information, but what I am going to do is I'm going to go over the 4.2 kinetic energy homework from Monday. And I'm also going to go over the 4.2 potential energy homework that was due this morning, that was assigned yesterday on Tuesday. All right, so let's do the kinetic energy homework first. And the reason we're doing this is because the assignment, this will hopefully be a short video, and the assignment that you're going to do today and tomorrow is you're going to be working on some practice with kinetic and potential energy. All right? Okay. So, how can we determine if an object has kinetic energy? Well, remember that kinetic energy is the energy associated with movement. So, if an object is moving, it has kinetic energy. The object is moving. Obviously, your answer needed to be a little more grammatically correct, or, sentence. You needed to write a sentence here. But the object is moving, basically. That's how we know that object has kinetic energy. Number 2 says that a baseball with a mass of 0.15 kilograms is moving at a speed of 40 meters per second toward the batter. What is the baseball's kinetic energy from this motion? So for number 2, we needed to write our knowns, unknowns, and equation. Our knowns are, we know a mass equal to 0.15 kilograms. It's moving at a speed towards the batter, so that's also known as a velocity, because we have a speed and a direction, right? So, we have a velocity of 40 meters per second, 40.0 meters per second. What is the baseball's kinetic energy? That's what we're looking for from its motion. From way long ago, does anyone remember what the equation is for kinetic energy, since that's what we're looking for? You'll recall that the equation is kinetic energy equals 1/2 mass times velocity, and that is squared. All right, so since we don't need to rearrange anything here, we just need to plug everything in and solve. That was a nice and simple problem. So we're going to take this equation that we have above, and we're going to put it here, and we're just going to plug everything in and solve. So we have 1/2 times the mass, which is 0.15, and it's in kilograms, so that's good. We don't have to convert it. Then we're going to put in our velocity, meters per second, and we will square that. And when we plug this into the calculator, we find that we have a kinetic energy of 120 kilograms times meters per second squared. Another way of saying that is joules. Okay, so there was our answer for the first one here. Or for number 2. Now number 3 states that a 1,350 kilogram car doubles its speed from 50 kilometers per hour to 100 kilometers per hour. By how many times does the kinetic energy of the car's forward motion increase? Well, you could have done this mathematically, or, well, let's just do it mathematically and then we'll look at the or, okay? So we have to figure out, we want to know how many times does the kinetic energy from the car's forward motion increase. So what we need to know is the car's forward motion at the beginning and the car's forward motion at the end. So let's find it at the beginning. The mass is going to be the same no matter what. Our initial velocity, our first velocity, is going to be 50 kilometers per hour. But we have a problem here. We cannot have kilometers per hour, right? So we need to convert this to meters per second. And we can do that by dimensional analysis. How many meters per second is 50 kilometers per hour? Well, we know we'll do kilometers per hour first. We know that 1 kilometer is equal to 1,000 meters. We can cancel kilometers. We're good to go. Now we have to do hours. We know that 1 hour is 3,600 seconds. Can cancel hours and hours, and we're left with meters and seconds. So now we're good. We can multiply everything on the top, divide by everything on the bottom, and we get about 14 meters per second. All right. So we want to know, what is the kinetic energy first? What is our first kinetic energy when the car is only going this 14 meters per second or 50 kilometers per hour? We're going to use our same equation. We're going to plug everything in there and solve. Kinetic energy is equal to 1/2 the mass, which is 1,350 kilograms, times our velocity, which is 14 meters per second. And when I plug that all into my calculator, oops, I forgot squared here. All right, now plug it into my calculator. I get a big, huge number. I get 132,300. That is joules. If you wanted to write this in kilojoules, you could do that. How many kilojoules equals, not kilograms, kilojoules is equal to 1,300 joules. Well, 1,000 joules equals 1 kilojoule, just like 1,000 anything equals 1 kilo anything. Joules cancels, and we get that 132.3 kilojoules. Either answer is correct. If you want to leave it in joules, that's fine. If you want to convert it into kilojoules and really impress me, that's fine too. So that's our first kinetic energy. What about our second kinetic energy? Because we want to compare our how much energy is associated with this car traveling at 50 kilometers per hour first. So this is the kinetic energy associated with it initially. And then we want to compare that to the kinetic energy associated with it when it's traveling 100 kilometers per hour, right? So our mass is going to stay the same. We have 1,350 kilograms. Our velocity, though, now is 100 kilometers per hour rather than 50. So we'll have to convert that to meters per second, the same way that we did before. So we're going to say kilometers to meters first. We say 1 kilometer equals 1,000 meters. This. All right, then we're in meters and we're good to go, but we need to convert hours, 1 hour to seconds first. Hours. All right, so from this we get about 28 meters per second, which makes sense, right? That makes sense because we were at 14 meters per second, and then we doubled our speed, and that makes sense. Perfect. We went from 50 kilometers per hour to 100 kilometers per hour. We went from 14 meters per second to 28 meters per second. That's exactly doubled. Perfect. Let's do our unknown, which is the second kinetic energy, and we're going to use our equation that we have been using the whole time. And then we just plug everything in and solve. So here we have 1/2 times the mass again, kilograms, times the velocity in meters per second, and we will square that. We plug this into the calculator, and we get a big long number again. This equals 1,000, not 1,000, sorry, not even 1, Miss Montgomery. Okay, that equals 529,200 joules. Another way to write that, we could do dimensional analysis. How many kilojoules equals this many joules? We know that 1,000 joules equals 1 kilojoule. When I put that in, cancel, I get that we have 529.2 kilojoules. So let us now compare these two values. We're going to compare this one and the one we just found. So let's go to this page over here. So when we are traveling at 50 kilometers here, we have a kinetic energy associated with that car of 132.3 kilojoules. When we double our speed to 100 kilometers per hour, we now have a kinetic energy of 529.2 kilojoules. So we doubled our speed, but we did not double our kinetic energy. What we did actually is we quadrupled it. And if you wanted to find that, you would divide 529.2 divided by 132.3, and you get that we have an answer of 4 there. So the kinetic energy associated with the higher speed, with the doubled speed, is 4 times greater than the initial kinetic energy of this kinetic energy. Why is that the case? If you look at our equation, we have a squared here, right? So we don't just double it, we quadruple it. We times 2, right? So that is why if you wanted to just look at the equation and answer it not mathematically, you could have done that, and you hope that you would have come up with 4 times greater than. But if you did not do that, if you did the math, that's not wrong either. I did the math so that we could examine and actually see that, yes, in fact, it is 4 times greater. So either way you did it was correct. All right, there we go. So by how many times does the kinetic energy from the car's forward motion increase? 4 times. All right. Number 4 says that a boy is running on a beach with a velocity of 1.7 meters per second, and he has a kinetic energy of 35 joules. What is the mass of the boy? We will do our usual. The mass of the boy is what we're looking for. It's unknown. We know that his velocity is 1.7 meters per second, and we know that his kinetic energy is 35 joules. So another way of writing 35 joules, since we know that our mass is going to have to be in, you know what, never mind. Forget it. We know that it's going to have to be in kilograms, so we're just going to have to keep track of our units and make sure that we have our answer in kilograms because we're looking for a mass. Okay, so the equation we have relating all of these things is the one we've been using. However, we're going to have to rearrange this so that we're solving for mass. So in order to do that, I'm going to divide both sides by 1/2 and v squared to cancel those two out. If I do that on the right, I have to do that on the left. Oop, not m, sorry, v squared. So I can rewrite this in, I'm just going to rewrite it like that. Kinetic energy divided by 1/2 times the velocity squared equals the mass. And that looks really yucky and complicated. So I think that you would know that we could also write this as 2ke because we have divided by, or 1/2 on the bottom, and that's the same thing as putting just 2 on the top, right? If we're dividing by something and dividing by something again, we can just put it up on the top. The 2 goes to the top. If you don't know that, or if that's too complicated for you, then leave it as how we have it written right here. But if you see this and you're like, oh, that's so ugly, I agree. So that's the correct way to write it, but either way that you do it is fine, as long as you get the correct answer. I think it's better to do it this way, less sloppy, and it just makes it a lot prettier and make more sense to me, but if it's easier for you to do the math like this, then I'm not going to tell you to do the math a different way, as long as you understand what you're doing. Okay, so we plug everything in. We get 2 times the kinetic energy divided by velocity squared equals mass. I have 2 times 35 joules divided by 1.7 squared. When I plug, and this is meters per second. When I plug all of that in, I get that mass is, I just had it plugged in. I get mass is 24.2 kilograms. So that is my answer for number 4. And finally, number 5 says, there is a basketball rolling towards a volleyball that's sitting at rest 5 meters away. So we have a basketball, and it's rolling. I'm going to indicate rolling with these motion lines. It's rolling towards a volleyball, and the distance between the two is 5 meters. There we go. I find that it's always easier to draw these things first before you try to, if you're just trying to do it verbally, it can be a little more challenging. So it's easier to draw a diagram. What are the two systems in the scenario? There are 2 systems in this scenario. What are they? First system, remember, a system is just anything we can put a boundary around. So the first system is the basketball. The second system is the volleyball. Which ball has kinetic energy? Well, we said that the basketball is moving, so the basketball would have kinetic energy. And it specifically says that the volleyball is at rest, so it does not have kinetic energy. It does have a type of energy. That's letter C. Which ball has potential energy? This one would have potential energy because it is at rest. It has the ability to move, but it's not actually moving. Okay? So that was it. That was the answer for number 5. And as long as you explained those things in your own words and it made sense, then you're good to go. Now let's do the homework that was from yesterday. All right, number 1 says, true or false, an object must be moving in order to have energy. That is false, because of that example I just showed you with the volleyball, or because of the apple in the tree, right? All of these have potential energy. Potential energy can be stored in an object that is not moving. All right, then you needed to give an original example, meaning one that I haven't given or that's not in your book, of a system that has potential energy. So any example of something that has the ability to be influenced by gravity or chemical potential energy, any kind of system that makes sense in the that it would have potential energy would be good. I can't really give you an answer for number 2 because it depends on what you wrote. But number 3, I can give you an answer. Number 3 says that Miriam's backpack is at rest on Mr. Porris's desk. The backpack is super full of textbooks and therefore has a huge mass of 14.5 kilograms. If Mr. Porris's desk is 1.10 meters tall, what is the gravitational potential energy of Miriam's backpack? So we will write our knowns, unknowns equation. The mass of the backpack is 14.5 kilograms. The height of the backpack on the desk is 1.10 meters. And we want to know what is the gravitational potential energy. All right. We do actually know one more thing that's not explicitly given in this question, but we know that because Miriam and Mr. Porris's desk exist on Earth, that's where we are. So we know that the gravitational strength is 9.8 newtons per kilogram. Now we can write our equation, which is GPE equals mass times gravitational strength times height. I don't have to rearrange anything. I just have to solve, plug in and solve. So I get GPE equals my mass, which is 14.5 kilograms, times my gravitational strength, which is 9.8 newtons per kilogram, times my height, which is 1.10 meters. If I plug this into the calculator, I find that I have a gravitational potential energy of, my kilograms and kilograms cancels, 156 newtons times meters, and that's the same thing as 156 joules. So my gravitational potential energy for that one was 156 joules. And finally, number 4. A goozy fruit is hanging from a goozy tree on a far distant planet called Montgomeronius. The gravitational strength on Montgomeronius is 3.5 times greater than the gravitational strength on Earth. Question A says, what is the gravitational strength on Montgomeronius? And I even gave you a hint on how to do this. I told you that the gravitational strength on Montgomeronius, which is what I'm going to call GM, is 3.5 times stronger than the gravitational strength on Earth. We know what gravitational strength on Earth is. It is 9.8 newtons per kilogram. Right? So if I plug this into a calculator, I find that I have a gravitational strength on this new planet of 34.3, and my units are newtons per kilogram. There's my answer for part A. Super simple way to determine that. All right, now that part B says, now that you know G on Montgomeronius, please determine the gravitational potential energy of the goozy fruit, which has a mass of 1.25 kilograms, if it is hanging from a tree at a distance of 4.50 meters from the surface of the planet. So for this one, you needed to write your knowns and unknowns and all that jazz. Okay, B wants to know, or B says, now that you know G on Montgomeronius, please determine the gravitational potential energy of the goozy fruit, which has a mass of 1.25 kilograms, if it is hanging from the tree at a distance of 4.50 meters from the surface of the planet. So for this one, we needed to write our knowns and unknowns and all of that jazz. Our knowns, we know that the mass, well, let's write we just solved for G on Montgomeryanius, which is 34.3 newtons per kilogram. We know that the mass of the goosey fruit is 1.25 kilograms. And we know that the height that it is above the surface of the earth, or the planet, not the earth, is 4.50 meters. We're looking for the gravitational potential energy of this fruit, so we're going to use the equation we've been using the whole time. And then we don't have to rearrange or do anything, so we just have to solve now. So we have GPE is equal to the mass, which is 1.25 kilograms, times the gravitational potential energy, gravitational strength, which is 34.3 newtons per kilogram. I had to move this down so I don't run out of room. And then we're going to multiply that by the height, which is 4.50 meters. Plugging all of that in, we get that we have a gravitational, the goosey fruit has a gravitational potential energy of 193 joules. All right, finally, part C says that a second goosey fruit is a little higher up on the goosey tree. If this second goosey fruit has a mass of 1.45 kilograms and a gravitational potential energy of 260 joules, what is the height from which the second goosey fruit falls? All right, so we'll just do C right here. We have our knowns. The mass of this goosey fruit is 1.45 kilograms. The gravitational potential energy of the fruit is 260 joules. And we know the gravity on Montgomeryanius is 34.3 newtons per kilogram. Our unknown is the height, how far up the tree this fruit is. And our equation is the same one we've been using. MGH. We have to rearrange this, though, for H. So we're going to divide both sides by mg. When I do that, I get that height is equal to gravitational potential energy divided by mass times gravitational strength. So now I just need to plug everything in and solve. So height equals gravitational potential energy, which is 260 joules, divided by mass, which is 1.45 kilograms, times 34.3 newtons per kilogram. And plugging that in, we get a height of 5.2 meters, which makes sense, right? Because I said that the second goosey fruit, if you want to check your answer, the goosey fruit is a little higher up on the goosey tree. So this second fruit is higher up. Remember that the first goosey fruit was at 4.5 meters up the tree. Now we're at 5.2. So that's a way that you could check your answer. I am a big advocate of going back and making sure that your answers make sense. Okay, so that is it for section 4.2. And for the rest of the period, for the next 15 minutes or however many minutes are left, you will be working on the 4.2 review questions, because this can be kind of confusing, and we really need to understand these concepts before we move on to 4.3. So depending on, you're going to work on those today, and that is it. So please let me know if you have any questions. We will start on 4.3 tomorrow, and that is all. Please let me know. Again, have any questions. Thank you.